Renal failure is a significant adverse event of comeback injury that increases mortality. It was present in over 50% of related deaths. Renal replacement therapy greatly reduces the mortality rate by 90%, eliminating excess potassium in circulation in absence of a functional kidney. The increased potassium levels result in a widespread cell death, causing release of intracellular potassium into the circulating, resulting into a state of hypokalemia. The goal of our prototype is to build a bridge dialysis system that can be used to reduce the circulating potassium levels in an injured person with renal failure and return potassium levels to 5 millimoles. Our features and design constraints consist of a system that contains the sorbent and can be interfaced with the patient in a manner similar to what is seen in the conventional dialysis. Secondly, the system is supposed to be made to be compact. And thirdly, preliminary studies that shows that the sorbent is not toxic and in direct contact with the sorbent is fine. To create our bridge dialysis system prototype, we use the rectangular base that encases 3 rectangular sorbents positioned at the center of the system to collect potassium from the blood as it flows through. Tubing is placed on each side of the bridge dialysis system. The tubes are designed to distribute flow across the entire surface area, ensuring that blood passes through the full volume of the device. One tube allows blood to enter the system for potassium removal, while the other allows blood to exit with a reduced potassium concentration. Both ends of the tubing are in theory connected to the patient to cleanse and return the blood.
Number 1 asks us to find the surface area for potassium removal given our designed sheet arrangement. In our design, we arranged the sorbent sheets horizontally inside a cartridge measuring 10 centimeters long by 5 centimeters wide by 5 centimeters tall. With this configuration, we found out that we had a maximum of 4 possible sheets, as 5 or more would completely block blood flow, which would kill any patients. To determine the area our blood would travel through, we subtract the area occupied by the sheets, giving us 4 0.5 centimeter gaps. Calculating for flow velocity, we use the equations for flow rate in the continuity equation. Q is equal to AV, and A1V1 is equal to A2V2, where Q is the flow rate, 500 centimeters cubed per minute, A is the total cross-sectional area for flow, and V is the velocity. The area available for blood flow is based on our 4 gaps, each measuring 0.5 centimeters wide by 5 centimeters tall, giving us a total flow area of 10 centimeters squared. Substituting to find V, we have velocity is equal to 500 centimeters cubed per minute over 10 centimeters squared. This gives us a final velocity of 50, our maximum allowed velocity. Next, we calculate the surface area by taking the 2 sides for each sheet, multiplied by the length of the sheet, 10, by the width of the sheet, 5, times the total number of sheets, 3. This gives us a total surface area of 300 centimeters squared. Number 2 asks us to calculate the potassium removal rate, little j. Using the flux equation, we take our given big J of 0.2 millimoles per centimeter squared per hour and multiply by our surface area of 300 centimeters squared, giving us a little j of 60 millimoles per hour. Dividing by 60, we get a final removal rate of 1 millimole per minute.
Number 3 asks for the outlet potassium concentration, and so first we started out by drawing a diagram with flow rate and concentration in, and then flow rate and concentration out. So to solve this, we have to do a mass balance, which means mass accumulated equals mass in minus mass out plus mass generated minus mass consumed. And there's no mass generated or consumed, so it's just going to be accumulated equals in minus out. And mass accumulated in this case is actually equal to little j, which we calculated above, which is 1 millimole per minute. And then Q in is going to be equal to 500 centimeters cubed per minute, and to convert to liters per minute, it's going to be 0.5. C in is also given, it's 8 millimolar, and then Q out is the same as Q in, and then C out is what we're solving for. After putting all these values in, we get a value of concentration of potassium out equals 6 millimolar. And then for number 4, it's asking if our potassium concentration will go back to normal levels after 1 pass, and the answer is no, because after adding 3 sheets, the concentration becomes 6 millimolar, and a normal level is below 5 millimolar. And then number 5 asks how long it will take for 5 liters of blood to undergo a single pass. And to do this, we're using the flow rate, which is 0.5 liters per minute, and dividing that 5 liters by that flow rate so that the units become minutes. So there's going to be liters divided by liters per minute, and then we get a value of 10 minutes. Number 6 asks how many passes do you estimate you will need to get back to normal potassium levels? And what we calculated was that we would need 2 passes, because after 1 pass, the potassium level is 6 millimolar, and if you do 2 passes, the second pass will make it go down all the way to 4 millimolar, which is within the range of healthy.